In 3.6, our goal is to use derivatives to analyze graphs of functions. Let's begin with why do we even need derivatives? Back in the day, we got a function, we made a table of values, we plotted points, and we connected the dots. And there you go. We've graphed our function. Why do we need calculus? Well, we could have a nice smooth curvy connection of the dots, but that's only knowing certain points. That's not every single point in the graph. This is what it could look like. Maybe there was an asymptote here and we didn't know it from the table. Maybe there was a slight change in how the slope developed throughout the graph. Maybe there was changes in concavity or increasing, decreasing between points that we plot. We have no idea until we use the calculus. But we're going to start doing this curve sketching with some very simple functions. We're going to do 3 examples. Here are the steps that you usually want to go through when sketching a curve. Think about your domain restrictions. Find any asymptotes. Those usually go together with domain restrictions because of the vertical asymptotes, but horizontal and slant may exist as well. Finding x and y intercepts can be helpful. Then we use our derivatives. The critical points, the intervals of increasing, decreasing, and relative extrema, that's using the first derivative. The intervals of concavity and the points of inflection, that's using our second derivative, and using all the information from above and putting it together. Going back to just talk about these, so the asymptotes and the domain restrictions usually we do together. Remember, the vertical is where the denominator equals 0. The horizontal, think of our degree shortcuts. Okay, limits can be helpful too as x approaches infinity. Slant asymptotes you're going to have if there are no horizontal asymptotes and the degree of the numerator is greater by 1 than the degree of the denominator. X and y intercepts, you know where y is 0, where x is 0. So let's do 3 examples. We're going to sketch the graph of the function, making sure to label everything, any intercepts, any asymptotes, any relative extrema, points of inflection, everything that can help us tell more about the function. And then we can check with the calculator if we want to. So first, I'm going to think about the polynomial. Are there any domain restrictions? Are there any asymptotes? No and no. So let's move on to the third part of that, are any x and y intercepts. Well, the easiest one to do first is when x equals 0. Those are the y intercepts where x equals 0. So when x equals 0, if I plug 0 in everywhere, I get 0 cubed, 6 times 0 squared, 9 times 0 plus 1, I get 1. So here's a point on my curve is 0, 1. Helpful point. I'm going to highlight or circle all of the essential things that I want to put in my graph. Any points, any asymptotes, any maxes, mins, things like that. I'm going to highlight those so that I remember to go back and put them in. Now what's not as easy to do is the x-intercepts. That's where y is 0. So if I set this equal to 0, I want to think about would I be able to factor it. I can't quickly or easily do that, so I'm going to skip that because I don't necessarily need those intercepts if they are there, but they can be helpful. So now we move on to what the derivative tells us. So now I want to find f prime, 3x squared minus 12x plus 9. There's my first derivative. And what do we do with our first derivative? Find the critical numbers. So where does the first derivative equal 0 or not exist? Equals 0 if I factor out the 3. And my factors x minus 3, x minus 1 give me the critical numbers of 1 and 3. So I make my number line with 1 and 3 on there, and I test the first derivative. So first derivative is what I'm testing here. So f prime, when I plug in 0, I'm looking at my factors of the first derivative. When I plug in 0, and please remember the first derivative, that includes what I factored out. Plug in 0, negative, negative, so that looks like a positive. Then between 1 and 3, like 2 gives a negative, and then after 3 gives a positive. So what I know my function will be doing is increasing then decreasing, then increasing. That's what the first derivative tells me. Because I have no restrictions, I know that I have a relative max at this value. So a relative max is at 1. What's the y coordinate? Well, we have to plug that in. Plug in 1 into the original function and come out with 5. F of 1 equals 5. Another spot of something critical happening is at 3. This one is a relative min. The x-coordinate is 3. Plug in 3 into the original function. 3 plugged in here gives me 1. So 3, 1 is a relative min. So again, points that are essential, I'm highlighting, I'm circling so that I notice them. Now I move on to the second derivative. What is the second derivative going to tell me? So my second derivative, f double prime, looking back here, it's going to be 6x minus 12. Again, set it equal to 0 for my PPOIs, my possible points of inflection. Doing some factoring gives me 1 PPOI at 2. So I'm put 2 on my number line, and now I am testing the second derivative. So f double prime. F double prime with 0 plugged in looks like a negative. With 5 plugged in looks like a positive. So I know second derivative tells me concave down, concave up. Therefore, I do have a point of inflection at 2. So point of inflection is 2, and the y coordinate, plug in 2 into the function, and 2 plugged back into the original function gives me 3. So the point of inflection is 2, 3. Here's another important point I want to put in my graph. So now that I've gone through both derivatives, I found maxes and mins and points, I'm going to plot them on my graph. Now let's think about putting our axes up here wisely. Points like 2, 3, 1, 5, 3, 1, not such big points, and no negative points. So I'm probably going to put my x-axis fairly low and my y-axis fairly close to the side. And then I want to space it out so that I'm maximizing my space. So I notice that my x values only go up to 3 at the biggest. So if I count by two blocks, 1, 2, 3, that's really not giving me much. Maybe by every 4 blocks, but I'd like to be even on the x and the y axis. So what's my highest y coordinate? It's 5. So let's see, if I do 1, 2, 3, 4, and 5, that looks like it should work. So we'll keep it even on both sides. 1, 2, 3, 4, and 5. So that's where y is 5. Let's move this out of the way a little bit, and we can relabel this the y-axis up here. Okay, so we do want to space it out similarly here. 1, 2, 3, so that our graph really isn't distorted. Now let's plot the points that we deemed essential, like the intercepts 0, 1, relative max at 1, 5. As we plot the point, let's label that it's a relative max. That'll help us when we're connecting the dots. 3, 1, and we want to label that that's a relative min. Notice that if it's a relative min, I can label below it because I won't need to go in that direction. And then a point of inflection at 2, 3. So I'm going to label here that this is a POI. That'll help me with the curves when I connect the dots. So now I'm going to connect the points and make a smooth curve. So if this is a relative max, I need to go increasing to decreasing. If this is my only point of inflection and I start with concave down, then I want it to be really clear that this is concave down up to here. Okay, now I can keep going in this direction. Then I need to change concavity, so now be very clear that this is concave up. Don't be sloppy with the graphs. Show me what you know about the concavity.